So welcome to this class of IC and VLSI Design EI331. So in this class we will discuss about the IC design flow and the VLSI design styles. And apart from this, connected to this, we will also discuss the design methodologies, the various VLSI or IC design methodologies. We'll take an overview of that, and then what are the manufacturing trade-offs we have to do. Then VLSI design cycle, or in general that is also called the IC design flow. And then then we'll see that for a good design, what things we need to take care of. So this is considered under structured design principles. Then we'll also see what are the various design styles. It is connected to the design methodologies, but somewhat like design methodologies in the first thing we will give a little perspective, and then we will see the same thing in detail. Then when we have designed the things, then what are the design quality matrices which we should use, and like what is the trade-off between them. And then we will also see that what are the various type of power dissipations we compute. So this is also a sort of lecture in which you will get the things little bit in depth of what we have seen in the last class. So let's start with the overview of the VLSI design methodologies. So in VLSI, basically whenever we design something, some circuit or some IC, so there are two options we have. Like it is whether we want to design everything from scratch, all the transistors, all the wires, connecting wires, interconnects, and the pads, and whatever you require. If you have to design everything from the scratch, if the engineers design everything by their own and optimize the things, then it is called the full custom design. Each of this full custom design and the semi-custom design have its own advantages and disadvantages. But which one should be used depends upon the application. So we'll see the advantages as well as the disadvantages related to them. So this is like this chart which you can see here is between, on the x-axis this is design time. So how much time is taken to design the circuits in each of them, in each of the technology, in each of the design methodologies. And then related to that, on the y-axis you will see the circuit performance. So if we choose like a full custom design, and the other one is the semi-custom design. So the full custom design is the design in which the engineer design everything by his own. And in the semi-custom design, what the engineers do are like they use the library which are like previously built into the software, okay, or into the simulation tool. So those standard cells are used to design the if are used to design the targeted integrated circuits, then that particular method is called the semi-custom method. So if we try to compare them together, then the full custom design have like more opportunity for better performance, isn't it? If you design the things by your own, so then you can optimize the things by your own. Then the area which the circuit will take will also you can optimize. The power dissipation it is going to consume also, that you also can optimize. The delay which will be there, by reducing the wire lengths and all those things, you can reduce the device the delay as well. So you can like completely do the things by your own and optimize the circuit at its fullest level. But the downside is if you do all these things, obviously it is going to take more time. So the in case of full custom design, the design time, okay, until the circuit is like can be commercially available, okay, or can be commercially fabricated, for up to that level, to reach up to that level, it needs a lot of time. So the design time is high. So the design time required is more compared to the other methods. But the good thing is you can have better performance or the good performance. But if we consider the semi-custom design, which you can see the other graph here. So in the semi-custom design, if you'll see, so the semi-custom design, although the design, because you are using in the semi-custom design, what we do, the same circuit what you have, let's say, designed for the full with the help of full design methodology or using the full design method, full custom method. If you design the same circuit with semi-custom method, then the time required will be less, because you are using the standard cells which are available into the library of that simulation tool or the software tool. Okay, and later on you will fabricate it. So the standard cells are used. So obviously the design time will be less, but the bad thing is that it will have like poor performance. You cannot optimize the things, all the things, because whatever is inside that cell which you have used from the library, you are not going to optimize it, right? So if you are not going to optimize it, then the performance, the performance of the overall circuit will be little poor than the performance of the full custom design. So these are the, like, you can compare them. But obviously the time is the good thing which you got is, if you want to design the things quickly, or if you want to test something at the because the time is also important, plays an important role in case of VLSI circuits, or whenever you have to do any commercial like application. So time also plays an important role. So for those cases, you have to like use both of them. Okay, so in the standard, in the industry, the standard is like good companies, or for like particular applications, if they are using, they use full custom design, and if it is for general application, then people also use semi custom design. So it depends upon, it is like application dependent, which type of method you will use. It is not like only full custom method is always used. So this what is about, and this we have already discussed. No, I mean, this we have not discussed. So you see, when we design the things, let's say one of the technology we have chosen, one of the design method we have chosen. Okay, whether it is a full custom design or a semi custom design. Now there is another aspect is like depending upon the Moore's law. In every 2 years, what happens? The design complexity gets double, or the the number of transistors which you can fabricate in the same area becomes double. So what happens? Okay, so I mean, when you are moving from one technology to the another technology, what the ideal case should be, like this red graph which you can see here. Okay, this graph you should follow, that once you have designed the circuit optimally, like this region, if you can see here. Okay, so this region, so you should have ideally designed the circuit at its optimal level, whatever like method you are using. By that method, optimally design the circuit at its best, get the best designs, and then you start the production cycle. So the later half, you can see this whole is like production cycle. But what happens if you will do this, then the design time will be longer, and you in the next technology, because you see, if you have taken like 1 year or 1.5 years in designing the things, then the cost will also increase, and you will not be able to get all the cost whatever you have put into the company to produce that particular product. You will not be able to get that complete amount of the complete returns from the market. Okay, so the company will be in the loss. So the ideal thing should be, you design the optimized things and then use it up till it is like it is not completely, all the applications related to that particular IC is not exhausted. So use it up till that time. But if you will do that, then the other companies which are like the other competitors will come up with a new with the updated version connected to this Moore's law. So they have the finer technology, and with that the applications they can perform, or like the applications which they can do, or the computational power which they will provide to the customers will be higher. So you will lose in that aspect. So what people do is, rather than following the complete technology, complete technology, I should say, complete technology, what I mean, you should say, the complete technology, this full advantage of that technology, rather they restrict it to certain limited time. And what they do, they give less time for designing the things completely, and if it is not yet optimized, then they go for the production. Once the production started, then whenever like they feel that the another competitor will come up with a new idea, or will have the increased complexity, I mean the increased computational power, then they move on to the another technology, okay, the final technology, the next technology. So then the design window, the design is not used at its full advantage. So I mean this is what usually the people follows. So you see, in the same next slide, you will see that actually this is what the people follow. But in this case, what happens? The design time is also like you have reduced the design time. The production time is like the limited also, so that you can take the advantage of the of whatever you have done, and you survive in the competition. But the problem is you miss some technology window. So that is what the lower side is. Okay, and for the same applications you use the higher version. So that is what they think. So usually this particular technology is better strategy. So this is what the strategy usually the companies follow when they are doing the things at the commercial level, rather than following the ideal way. People follow these things. Okay, so this is what the same diagram shown in two different perspectives. Now let's move on to what we call as the design flow. So in the design flow, if you just consider, so here we will discuss that how actually what is the process to design the ICs, integrated circuits. So this we have already seen. So this part particularly is like is almost the same what we have discussed in the last class, but in a different perspective. So I'll cover this thing in short, and we'll try to give you a little different perspective from what we have seen in the last class. So what we do is rather, this is also called the IC design flow or the VLSI design flow. So what we call is, what we do, we start with this system specification, and then after having that system specification, what we do, we design its functionality. When we say its functionality, it actually means how it is going to behave. Okay, so what functions it is going to use. So then the functional architecture we write. Okay, or then once the functional architecture is written, then we verify it. So this is like backtesting, again and again the same thing. Once the functionality is completed, then you go for the logic design. When I say functionality, it means that, let's say yesterday I have given you the example of designing a machine which can like automatically, or the electronic mop. So that is the behavior which you want. So that yesterday I have explained you that it should clean the floor. Okay, so that is what the functionality you want. Then to do that, what you will require, so that is called the functional architecture design. Now when you do that, okay, so you will think that there should be some brushes, some movement, some moving parts should be there. Okay, or some other person will come with a certain different idea. Okay, he may come up with some like vacuum cleaner sort of small vacuum cleaner sort of idea. So there can be multiple ideas. So he will see that what are the functions which various blocks will do there, and then after that functionality is decided and like verified multiple times, then they go for the logic design, right? Then the logic verification. So logic design, logic verification means that at the gate level we are talking, right? Then after that particular thing is designed, then you go for the circuit level. Okay, that which gate will be connected with which gate. So logic verification, and then the circuit design. So okay, so then you go for the circuit design, and then go for the physical design. So which particular block should be placed near to which other block, so that the delays and the other parameters which you have already discussed should be like minimum, or whatever parameters you want high, they should be high. So this is what the general flow is. Okay, now the same flow we will discuss with the help of this diagram. So you see, I mean, I just wanted to show you like how it will look like. So system specification, you get the specification either by your own or by your clients. Then you write the algorithms, then you get the gate level circuit. Then from the gate level circuit, you actually design the circuit. Okay, considering the library, either the available libraries or the full custom method. Okay, so whatever method you are using. Then once that particular thing is done, then you extract and verify the parameters, that whether you are getting all the things properly or not. Whatever parameters you have decided, the design parameters you have decided. So are you able to get meet those constants or not? So that you do, and then once the things are over at that level, then you go for the physical verification, okay, or the physical synthesis level. So then the layout is generated. In this diagram you will see that the layout is generated, and then the layout, after the layout is generated, layout is nothing but a diagram showing that which region is having the N MOSes, which region is having the P MOSes, where the wires will be there, where the gates, these gate terminals will be there. So that is how you show them and try to show it, make it in such a way that the area which it takes it is like minimum. Then once that is done, then you go for the fabrication. Okay, that once that physical verification is verified completely, physical synthesis is done, then we go for the fabrication. And once that fabrication is done, then we take the pieces from each of this wafer, and then this particular each of the die is then put in the this packaging sort of thing, and then it is packaged. Okay, so this is what the IC design flow is. Okay, and the same thing is also like you will see this in the usually in the books also under the name of Y chart, okay, or the Gazaski's chart. This is also called the Y chart or the Gazaski's chart. So in the previous slide we have seen the general flow, but the same flow can be classified or can be differentiated into three domains. Whenever you are making an IC, so you are actually doing three things. What are those three things? That particular this diagram shows, and that is why this chart is so much popular, that it actually classifies the all whatever you are doing in the previous case in three domains. Okay, so these three domains are behavioral domain, okay, structural domain, and the geometrical layout domain or the physical layout domain. So this is like very clear now that how you are going to do. So let's see with an example that how we will do it. So what we do is, let's say at the behavioral level, first people will write some algorithm, okay, write the functionality for that thing, okay, whatever they require. Then once that functionality is they have optimized it and back tested it many times, that whether this is what they want or something else they want, or whether this particular algorithm will work in this direction or not, in this way or not. So okay, so this algorithm you will write, then you will say, let's say you are making it for, let's say, processor. So you will see that how many functionalities you want. So what will be the algorithm to calculate a certain thing, like in the microprocessor you want a mathematical microprocessor you want. So you want multiplication, addition, subtraction, and not only that, but let's say suppose you want logarithmic functions, exponentials. Okay, so the basic functions, whereas the advanced functions also. So in that case, what you will do, you will see that to calculate, let's say, exponents, how many times you have to do the perform the additions, okay, or multiplications. So then that multiplication loop will be used, but it will be used multiple times, okay, and how many times it will be used to calculate this particular thing. So for that you write the algorithm. Then once that is decided, then you go for the processor. Then processor, let's say this is for the processor. So you are writing the processor for the you are writing the algorithm for that processor. So that algorithm will be called as the behavioral behavior, or you decide the behavior of your processor. So that is what the behavioral level is. Then you actually see that in the processor what are the various blocks which you will use. Okay, so that is the structure. Multiplication block will be there, addition block will be there, some other blocks, subtraction blocks. So addition also you can do by subtraction, subtraction you can do using the addition. Okay, so what sort of things you want. So that is how you will see that which particular blocks will come in the processor. Then in the next stage, what you will see, that to optimize, to get the optimum design, the various blocks which you have designed should be at the optimal places, so that the parameters which you have already discussed should be minimum. So then you do the chip floor planning. So chip floor planning means the broad level at which you are deciding which modules will be placed where, which broad blocks will be placed in which regions. Okay, so that is what we design, and then we keep on moving on to the lower levels. Okay, so once that is designed, then we also need to have a controller to control that. So that controller, in case of VLSI or this particular digital circuits, it's called finite state machine. So then you design the finite state machines. So the basic idea is you start from the broad level, and at each of the lower level, you will have all the three domains. So you can classify them in behavioral, structure, and the geometrical layout. And at the lowest level, what you have is like the mask you get. So first you get the Boolean equations you get. Then from that Boolean equations you use the standard cells. So which are the standard cells are called the leaf cells. So then after the leaf cells are designed, then you place them this small standard library cells also. Okay, and these leaf cells are nothing but your this gates only. Okay, so if in a certain software that particular logical gates are available, so those logical gates are here termed as the leaf cell. Leaf cell can be anything. Okay, in case of digital circuits, you call these are gates. Okay, logical gates. But in other circuits also, this can be, in analog circuits also, you can use the standard leaf cells. Okay, and once that are done, then you place them, and then once those things are placed properly, then you go for the transistor level diagram and then the mask. So the final layout is done. So if you follow this particular approach, then it is called this is what the general procedure we follow. Okay, and this particular procedure is not only followed for IC design flow, but it is usually followed for any product. So if you, let's say, design any other product also, then usually we follow the same thing. We decide its specification, and then we move on to the lower levels. Okay, that how the things will be designed. So let's say, suppose you want to design a table. Okay, so in that case, suppose someone, you are the first one who are designing a table. So as I am telling you table, so you are knowing that what the table is, so you are able to understand it, the meaning of that word. But suppose you are designing the things at the very first time, then you even don't know what the table means. So what you will see is what actually the specification of the structure which you want, right? So you will see that that particular thing, the table or a particular structure, will be used to keep something or to used for study. And then you will see that, you will try to find that that particular structure will be used for what purpose, whether it is used for an old man to sit, for a young boy like a kid, or for someone else. Okay, so then depending upon that, you decide its height, okay, its width, and in which area it should be kept. It should be kept in a broad hall, in a hall or in a small room. So depending upon that, you decide its specifications or the dimensions of the table, right? Whether it should be used in the classroom. So you see, there can be many perspectives. How many people are going to use it? Like 2 people simultaneously in the classroom, or a small boy. So depending upon that, you do the specifications, and then you design the various components of that. So in case of table, you will design its legs, okay, then the upper platform, and then you will see whether the drawers are required or not, or the cost, how much cost is the client want to spend. So what functionalities you can provide. So then you will see in the same table, let's say in the example of the table, you will see that whether you have the previously built drawers or the platforms or the legs available. If they are available, then you will use directly to them, okay, if they are meeting your specifications. So that is called the cell based design, okay, the standard library based design. But if those things are not available, then you will start from the you will have to design everything by your own. So then you will cut a tree, okay, and then make the legs out of that. Then you'll make the planks out of it, and then you will make the platform. Okay, so this is particularly is called the full custom design. Okay, so each have its own advantages and disadvantages, right? The first method will take less time, the other method will take more time. Okay, so this is what you do. Okay, so this is what is classified into various terms. Okay, structural domain, behavioral domain, and the geometrical layout domain or the physical domain. So every design, whatever design we do, whether it is an IC design or a general design, we have just seen that this particular things you have to do. Okay, let's move on to the another slide. So if you start from the algorithmic level, the application level, let's say first the idea is in your mind and then you go up to the mask level. This particular design method is called the top-down method. Okay, the top-down approach you are following basically. Okay, so system specification you have taken and then you have designed the this functional block and logical. So this is like top-down method. If you are moving from top in the VLSI design flow or the IC design flow, from the top to the bottom, towards the bottom, then it is called the top-down approach. If you are moving in the opposite way, let's say you have the basic libraries and you just want to use these basic libraries for some other applications. So then you start thinking in the reverse direction, so that this particular cells are available with me, then how I can use them. So if you start thinking like that, then it is called the bottom-up approach. Right? Now, actually the design, like what? They are like top-down designs or the bottom-up approach. Ideally, the designs are a mix of both of them. Right? So, the good designs are the designs in which you use a mix of both the top-down approach and the bottom-up approach. Why? Because you see, in case of like actual designs, you don't have to design everything by your own. Some of the things will be available and some of the blocks you have to design by your own. Okay, depending upon your client's approach, client's requirement and the funds he want to spend. So depending upon that. So there are two approaches which are there, which people see. So these are like, we should know these terminologies if you are studying this course. And excuse me. So you see, in this slide also the same thing, no need to repeat it, but shown in a different way, that when you do the architectural design or the functional design in case of integrated circuits, and if you are using VHDL or Verilog, then you can do the design in 2-3 ways. First one is called the behavioral design, then the structural design, and the other one is the data flow design. So what are this? I'm just introducing the words to you, that what these words are when you are using a hardware descriptive language to do the to write the hardware, to write the code for the hardware. Then this is like in three, the VHDL code can be of three structures. Okay, the Verilog code can be of three structures. These three structures are behavioral, structural, and data flow structure. So what are this? This behavior may you like decide the write the behavior of the algorithm, and then in the structure you write the gates, which gates are connected, or the logical expression directly. And in case of the data flow method, this is like they are almost similar, but there is a slight difference in them as well. So in data flow, actually the word is like how the inputs and output signals are, how the signal is actually flowing, how the data is flowing into the system. So depending upon that, if you write the hardware code, then it is called this, you classify them in these three ways. But anyways, whatever you do, the final thing is like you get some logical expressions, and then from that logical expression you design the circuits at the gate level, and then from the gate level you design the transistor level circuit, then you physically place them properly and then fabricate and package it, okay, and test it, right? So the same thing. Now again, we will not go into those all things because we have already discussed them in yesterday's class. So the thing is like you have to, like whenever you are designing something, so which factors you have to do is you have to consider its performance. In performance there are like various parameters which we'll see later as well, then the functionality, and then the physical dimensions, the die size. So functionality is like whether it is working properly or not. First we have to verify that. Once it is verified, then we see the performance, whether all the things are getting all the performance parameters, speed, power dissipation, delay, whether they are getting them or in the right perspective or not. Then we will see that what is the die size. Okay, so depending upon the technology which you are using, technology which when I am saying it is the, or the feature size when I am saying, it means that what is the gate length you are using. If you are using a 1 micrometer gate length device, then it is called a 1 micrometer technology. If you are using 0.5 micrometer gate length, then it is called the 0.5 micrometer technology. So nowadays, if you'll see that it is like 11 nanometer technology people are working, or 7 nanometer technology they are working. So what does it mean? It means the length of the gate, or the distance between the source and the drain region of your MOSFET is like 11 nanometers or 7 nanometers. So whatever is the feature size or the technology size of your devices, or the technology in which you are working, this is actually this number. So this is what the number is. Then same thing. So architectural design, the examples are given, various processes. Then behavioral. So in the in case of behavioral design, what we have to do, we have to write the behavior of the logic. So this is how the in VHDL or this Verilog code will look like, will look something like this. Okay, and you generate some this. So we have this already discussed them. So I'm not giving these time, because the purpose is not to study the hardware descriptive languages in this course. If this purpose would have been, we have included this. Okay, but in some of the courses we do this, so that is why this particular slides are there. Okay, so in the this is what logic design. So then these are the design styles which we have already discussed, and physical layout. So this is the layout which we get. So once we draw this physical layout, then it is fabricated, and it is fabricated at various levels. So there will be multi-layer ICs, and for each of them you have like simulation tools with you, because you see, as I have already told you in the last class, to do the things manually is very difficult, because the things are so small. In one of the diagram yesterday I showed you that, right? Then once these all things are done up to the this fabrication, because these are all automated processes, you don't have to even touch them manually. So then once this is done, then you fabricate the things and then package it. Even for packaging also, there is like automation things which are available. Okay, now let's move on to the things which is like, once the design is completed, then we have to see that whether the design is good or not. Okay, so the broad idea is, the things which you should keep in mind is that, first thing is that the design, whatever you have designed, should work satisfactorily. That is, the functionality what you have desired should be available. And the second thing which you should keep into mind is, the complexity of the circuit should be minimum. So two things, functionality and complexity. First you should think about them. Then once these things are there, then you have to see about the other things, whether it is performing giving the performance parameters, or like the quality matrices, whether it is satisfying those quality matrices or not. What are the quality matrices? We'll see them later. Okay, so two things we have to see, functionality and complexity. So how to reduce the complexity part? So that is what we'll consider here. To reduce the complexity, what we consider is called as the structured design principles. So the structured design principles are like, this is the basic principles which you have which the design engineers should follow while designing any ICs. What are those? Particularly the digital ICs. Okay, so what are these principles? These are like, there should be a hierarchy. Okay, there should be a hierarchy of the blocks. When I say hierarchy, it means that there should be a bigger module. In that there should be some sub modules. Okay, those sub modules. So this whole work, or whatever work, or whatever functionality you want to obtain, that functionality should be divided into sub modules. Like what you do when you do a certain project, so what you do, you divide the work among among your group members. So in that case, the group leader will see like what the things should be, what the aim of the work is, and then each of the group member will do that particular task which is assigned to it. So that is what is meant by a hierarchy, and this hierarchy is available in all the systems which you use, whether suppose you are running a business or running an institute, let's say. Okay, like our institute. So then there is a hierarchy. Okay, at the highest level, the principal or the director is there. Okay, then after that, the other deans, HODs, faculties, and then the other staff will come there. So there is a hierarchy, and everything in that structure, in that hierarchy, everyone have his like what work he has to do, that is clear to him. Okay, so that is why the hierarchy is required. So in short, you can say, a very popular word is divide and conquer. So you divide the work among yourselves and accomplish the things. So that is what they think is. So hierarchy you should consider about, and we'll see with this with the example. So basically four are these are the there are these four design principles which you should use, the structure design principles. First is the hierarchy, then regularity. So regularity, when I say, it means that the sub blocks or the modules which you are using there, okay, in the bigger block, so they should be like replicable. So you should be able to repeat them. They should be similar and should be simple as well. Okay, so they should be replicable. If that is there, then you call it regularity. And this is like in most of the digital circuits, if you'll see that this regularity is like there. Because if you're let's say designing a flip flop, okay, or a multiplexer or any other any other bigger circuit, so then you will see that the same block is used multiple times to achieve the task. Okay, so this like counters if you are designing. Okay, so the various D flip flops will be there. Okay, we have studied this in our earlier courses. So you see there are multiple D flip flops which will use. So that is what is called the regularity of the blocks. So the regularity should be there. Then there should be modularity. What do you mean by modularity? Modularity, when you talks about, it means that whatever blocks you have designed, the functionality of those blocks should be well defined. Okay, if it should not be like the functionality that particular block is doing multiple things. It should be able to do multiple things, but the whatever function it is doing, that should be well defined. If it is not well defined and it is not interfacing, it is not interfaced properly, then it is not a modular design. Okay, then one of the other thing which you should consider is the locality. When I say locality, it means that whatever like the signals or whatever the interference are produced into that particular block should be like constrained into that block itself, whatever sub module you are using. It should not interfere with the near neighboring blocks or the other far away blocks. If that particular thing is there, then you say, I mean, if it is not interfering with the other blocks, or if you are avoiding the long distance connections between them, so then the things will be constrained, or the interference between the components will be between a certain region only. So that locality should also be considered. That is why, let's say if in a block, okay, some logical gates are used, so you should not design the circuit or place the components in such a way that one component is placed at one part, I mean in one area, and the another components from which the signal will flow is kept far away from it. If that is there, if you do this particular thing, then the connecting wire will carry a lot of current, and it will like frequently carry the signal between them. So then there will be a lot of interference between this particular two gates and the other gates. So this should not be there. So then if suppose two logical gates are interacting too frequently with each other, then they should be placed together. Similarly, if two bigger blocks, okay, submodules are like interacting with each other frequently, then they should be placed together. That is what is meant by locality. Okay, so these are the things which you should consider. So with example, if you just consider, so let's suppose you want to design a 4-bit adder. So in case of 4-bit adder, what we do, we design 1-bit single adders, and then for each bit single adder we design carry and sum, and then these are designed by the use of AND and OR gate. So this is a simple hierarchy. So this is a simple example of hierarchy, what is meant by a hierarchy in this case, right? So this is what we do. Then regularity. Regularity is I have given you the example that we are using. Let's say in this case we are using I have designed a two input mux, okay, 2x1 mux, or a D flip flop. So in D flip flop, what we are doing, we are using inverters or the tri-state buffers to implement these things. Okay, so the same, whether it is a mux 2x1 mux or a D flip flop, we are using inverters and the buffers, tri-state buffers. So these are like replicated continuously. So then that is called the regular design. Then this modularity and locality I have explained you already. So these are the things. Now let's come back to the thing which we have started. So the design methodologies. So I have told you earlier that we have like a full custom design method and the the semi-custom method. So in the whatever type of design method you are using, so there can be various design styles which you follow. So whenever you design something, so which particular method you should follow, or what design style you should follow. So design styles, as I have told you, approach, full custom, top down approach, or the bottom up approach. So these are all mixed things. So you see, what are the various things which you have to see when you are designing the things. So there are four broad aspects in which you can divide the things. Performance, like how well the circuit is performing. Then the amount of area which the IC is taking. Then what is the cost which is involved to fabricate that, and how much time it will require to produce or to commercialize the product. Okay, so time to market. So these are the things which you have to keep into mind when you are designing a VLSI circuit. And to get this, there are various design methods or design styles which you can use to achieve your target. So these are like full custom method, standard cell method, gate array method, and FPGA method. So in semi-custom there are three methods: standard cell, gate array, and FPGA. And the full custom is another method. Okay, so I should have done one more classification level, but I missed that. So that is what I'm trying to emphasize. Now you see, when you use a full custom method, then you get everything best. The performance will be best, area efficiency will be best, the cost though will be high. Okay, and also the flexibility will not be there, because that particular full custom design or the application specific integrated circuit, ASIC here stands for application specific integrated circuits. So that particular circuit will work for that purpose only, application for that application only. Okay, so the performance will be good, area will be very less, cost will be high, but because you are optimizing everything, so time will be more, so salaries which you have to pay will be high. Okay, so depending upon that, the cost will increase and the flexibility will also be low. But the same thing, if you want to design with, let's say, standard cell based design, the gate array design, or the FPGA based design. So what are this? We will see in short. Okay, we'll see them. But the thing is that they will, if you use the semi-custom approach, either of the semi-custom approach, then the performance, you will not get that good performance. The area efficiency will not also be that good, but the cost will be reduced, and you will have the flexibility that if you want to just use the same cell for another applications, then also you can use. Okay, so there's just there is a compromise, there is a trade-off between them. Okay, you don't get everything good in a particular approach or in a design style. If you are using a particular design method, it is not like everything you get best. If you get one thing good, then the other thing becomes poorer. So we have discussed all these things, that what is the full custom design. So in short, if you'll see, so this is designing the entire cell by your own. Then you don't have any restriction where you'll place the blocks. Okay, you can optimize by your as per your applications, but it is too much costly, and it requires too much labor intensive work. Then obviously the designer should be expert in his field, VLSI domain, else he will not be able to design the things by own, because there is not designing the circuits, transistors only. There are various level interconnects, pads, so everything has to be designed. Okay, so this what about it, and how a full custom approach looks like. So here in this full custom design, you have designed everything by your own. Okay, you have not used anything inbuilt. Okay, so pads, wires, the various blocks. Okay, so everything is designed here. So this is called the full custom design. Then there is a standard cell based design. In the standard cell based design, what we do is we use the standard cells, the standard AND gates, OR gates, NAND gates, and then once these are used, then we use the connecting wires, or we call it routing. Okay, is done. So routing is done between the various channels. Okay, and then in this particular, the area will be more, because the standard cells which you are using will have the standard inputs, the standard dimensions of their own. So then the standard cell design will have this particular, then this is what it is. And in this case, how the design, just by a simple diagram, try to explain it. So what is this? You are using a certain cell libraries. So these are in the lower diagram, if you'll see. So these are the cell libraries which we are using. So let's say for cell A, if it is a logical gate, or if it is a sequential circuit, let's say a simple flip flop. So it can be cell A is, let's say, AND gate, cell B is a flip flop, D flip flop, cell C is like let's say T flip flop. Okay, so there are like various cell library cells which are standard cells which are available there into the library. So you are using them and making some connections between them and optimizing the circuit then later. So the performance will be little degraded. Then there is a gate array design. So in the gate array design, what we do is, rather than using these circuits directly, it is an array of gates. So something like PLAs. We have studied them in the previous course, digital course. So if you are using a PLA or a PL, then these are like gate arrays. So you are using these gate arrays and they are like programmable or non-programmable, and you are using them to implement the various your circuits, and you are customizing them accordingly. Okay, so you see, you are not completely designing the things, and these designs will be flexible because the gate arrays whatever you are using, whether it is a PLA or a PL, then they are programmable, let's say. So if they are programmable, you can test your prototype. Okay, this particular things, gate array design and the FPGA based design, are used for testing they are good for testing prototype designs. Okay, or if you are using the applications let's say for once, okay, or for twice, and if you just want to implement it, then once you want to implement it, then you can use these methods basically. Okay, but they have other applications also. So I have given you just the crude example that how this is done. So these gate arrays are designed, and these gate arrays are used to implement this thing. So you have like the cost will, because they are the standard available there only in the market. You can purchase a PLA directly, and you can use that PLA to implement, let's say, your project. Okay, the functionality whatever is required in your, let's say, project, you can use that FPGA or that PLA or a FPGA to implement that thing. So that is called your gate array design. Okay, so the cost will be lower, then the design time will be very less. Okay, but then the it cannot be used multiple times, or like there will be some restrictions as well. The optimization, the performance will not be that good. So in this case, what we are doing, these are, let's say, gate array design. So programmable, the examples for this you can get very easily from the digital electronics course. So in the digital electronic course, when we have designed some Boolean expressions with the help of PLAs, ROMs, PLs, that are all gate array based designs. Okay, so in short, I've tried to explain you here. Then you have FPGA based design. So what is FPGA? FPGA stands for field programmable gate arrays. So here, this is like in the earlier one also, PLAs and PLA, you have like programmable gates, but this have like more flexibility with comparison to that particular things. And here you have like this have more applications, and this is like vaster than what I should say the PLAs. So there is a little difference between them, FPGAs and PLAs. Okay. So here also the PLA FPGAs, again we have like various blocks which are called the programmable logic blocks, or CLBs, combinational logic blocks. So this combinational logic blocks are like we can write them, we can program them by various approaches. One of them is like the truth table approach. Okay, so you write them, and then once the circuits are built, then you test them. Okay, so the circuits also work properly there. So FPGA based designs are there. So in short, if you just try to summarize whatever we have seen so far, so there are various parameters like cell size, what is the cell type. So these all things, interconnects, area, performance. So these all things are like classified in for various design styles or design methods. So full custom design, you have like all the things good, most of the things good, but the cost is high, and it is not flexible. So otherwise all the things are variable in this. Whereas in the FPGA case or the gate array design, all the things are like mostly fixed, or you can program some of them. The area required is like also changes, the cost also changes. Okay, and the like what you have to do with this, how to fabricate them, so that also changes. Now let's move on to the last part of the this lecture, that is the design quality matrix. So when you are designing a IC, some of the things which you should see is like the design, the IC should have the ability to test itself, and this ability is called, because this nowadays these ICs are so huge and so many number of transistors are there, that if you try to check it manually or if you try to test them manually, then it will take a lot of time to verify all its functionality. So then in that case, that we design a circuit what is called as the built-in self-test circuitry. So this built-in self-test circuitry have like option to test the optimal cases for this, okay, or all the cases you can check. So this is like what is called as the built-in self-test circuitry. So in present designs, this is like unavoidable, that should be there. Okay, then we should also consider for the yield. So what is this yield? Yield is like how many good chips you have produced out of the total manufactured chips. If you have produced, I mean, if you manufacture, let's say 1000 chips, out of that only 100 chips are working properly, so then you will get a certain yield number. But if 900 chips are working, then you will see that your yield is better than the other one. But then the yield is also classified in certain things: functional yield and the parametric yield. When I say functional yield, it means that whether how many ICs, like out of all the manufactured lot, how many actual ICs are working as the desired functionality. So if let's say 900 ICs out of the 1000 ICs manufactured in a lot, 900 ICs are giving the proper functionality whatever they have designed for, then it is called like the functional yield is this particular number, 900 by 1000. Okay. Whereas in case of parametric, the yield is again defined like the parametric yield. This parametric yield is like out of all this the ICs which are giving you proper functionality, how many are fulfilling the desired parameters also. If let's say out of this 900 ICs, 800 are meeting your requirements, whereas the 100 ICs which were giving you the proper functionality, but the performance is not that good, so then the parametric yield is not there. Okay, so the parametric yield and the functional yield are defined into different ways. So you define, you should, I mean, these are the quality metrics, these are certain quality matrices which you should consider: testability, yield, then the manufacturability. So the manufacturability is like how many how many chips are actually following both the things. Okay, the ICs which are like giving you the parametric yield. So if the parametric yield is high, then the manufacturability is high. Manufacturability of the ICs of that particular process is high. If that is not there, then the manufacturability is poor. So when you talk about the manufacturability, it is related to the yield only. Then the whatever technology you are using, that technology should be updatable also. If it is not updatable, then what you are actually doing is you are shrinking or reducing the dimensions, but it is like not useful at the in the next stage. So you should not practice, because you see we have seen the Moore's law, but that Moore's law is not followed blindly. Okay, it is not like exactly in 1.5 years or 2 years the device dimensions will become half. It is not so. Okay, actually sometimes it takes 1 year to like do the things, to accomplish the things. Sometimes it becomes 3 years as well. So if you just if you're making the layouts and all the things in such a way that you are if you're using these all things, then your this particular design quality matrices should be like also see that whether your whatever technology you are using, whether it is updatable or not. If it is not updatable, if you are just shrinking the things without blindly, then it is not a technology updatable. So that should be there. Then once the circuits are designed, then we should also see whether they are reliable or not. So the reliability of the circuits gets affected by various reasons, and the biggest reason is, like in short if I say, it's the various points you can see here, but the gist of all these points is like there should not be a break between the wires, the connecting wires, or in the oxide which you are using there. So the thing is like they should not get deteriorated either with time or because of the high current or because of very high voltages which you have applied. So the things should be intact. there should not be a break between them. Whether you are using a oxide, whether you are talking about a hot carrier induced aging. So with time the circuit gets aged out and it doesn't works properly. Then there is electromigration. So if you are using like because of some noise or something at a particular place, there is like electrical current is or electrical voltage is applied continuously at that place, then electron can migrate from that particular thing. So that is called electromigration. Then because of certain high voltage or something electrical overstress, the electrostatic discharge may occur and there is a break between this or burnout. The ICs may burn out at a certain point at a single interconnect, or a certain breakdown may occur in a transistor also. Okay, so if in a whole IC anything is not working at a single point, is not working properly, then your whole IC is like become useless. Why? Because you cannot open this packaging and can resolder it or like change the component. Okay, so that flexibility is not there with integrated circuits. So that integrated circuits what you are using should be very reliable. So these are the various perspectives on which you check the reliability of the circuits. At the last we'll see that for the ICs we also have to see that what sort of like power dissipation it is having. So the power dissipation, if you talks about, so the power dissipation you check for dynamic power and the static power. So in the dynamic power is like it is like switching power or the short circuit power, or it is because of the glitching power. Okay, so we have to verify that as well, that how much power it is actually taking, and this power dissipation also becomes a very important aspect into this. So overall we should take care of the power dissipation, and this power dissipation can be classified into dynamic power and the static power. Dynamic power, as I have told you, is classified in 3 other ways, whereas the switching power is because of the static power is because of the leakage current. So the leakage current should also be kept minimum for a design. If it is not if it is not meeting these all requirements, then your design is not a good design. If it is meeting all these requirements, then your design is a good design. Okay, so that is what about those all introductory things in this lecture. So we have completed almost chapter 1 of your this CAN level ABC. So in the next lecture we will start with the MOSFET part. Okay, try to understand that MOSFET part, and later on then we will move on to the another part, which is like your fabrication and all those things. So this is what about today's lecture. So I hope you are able to understand it, and if you have any queries we can like talk in the class then. Thank you for listening.